Your test is next class. You have a study guide for it. The study guide is not giving you any practice problems because you've got those on all the homework quizzes and all that kind of stuff. But it is just reminding you of everything from the first 2 chapters that you need to know here, right? So you guys have had a little bit of time to look at it. As you look at that, is there anything that sticks out like, oh, I don't know what this is talking about? Yeah.
The significant figures
Yeah.
is the one that I got a little bit of trouble
Okay.
with in the homeworks.
All right, so there's some basic rules. Your textbook has them. Definitely go check them out.
Okay.
Do we hear for the notes on that?
I think I was gone. That was
Okay.
the class that I missed.
Okay, so if I've got like a decimal point here, then anything after the decimal point is going to be significant. Okay? So I'd have 1, 2, 3, 4, 5 significant figures. Okay? Does that make sense?
Yeah.
But if I had this number, these two are not significant. Okay? My 1 is, but my non-zeros trailing it are not significant. So this would have 3 significant figures. But if I had this, those become significant because of the decimal point.
Okay.
Those are probably the tricky rules that kind of catch you up.
Okay.
Part of it is like, how would I write this in scientific notation? Right, so that would end up me written just 6.0100 times 10 to the negative, or 10 to the 0. That's how that one would get written. Okay. This one, I'd write it as 6.01 times 10 to the 1, 2, 3, 4. But I wouldn't record those zeros there. Here, I would write, because that's there, even though these are really the same thing, because of that, I'd write it as 6.0100 times 10 to the 4th. And the reason that this period means so much, or this decimal point, is it's telling you that somebody actually, they didn't estimate, they're not guessing, they're not making stuff up. Somebody actually looked at this last number. Okay? Now, they may have had to estimate based on what they looked at, but somebody actually laid eyes on it in some kind of a measurement system. So I would just encourage you to go back and check those couple rules in your book. There's like 3 or 4 of them. You can even Google it. I mean, it's super simple.
Okay.
It'll come up real fast. And then you go back and look at those same questions and see.
It becomes easier.
It's definitely, I basically took the exact same problems and changed a number here or there, or moved a decimal point over 1 or something like that. So it's going to look just like that quiz. Okay.
We've had that before. All the other quizzes do.
It's going to look real familiar. There is some new stuff, but a lot of this is going to look very, very familiar.
Okay.
Anything else on here that you want to know about?
I just need clarification
Okay.
on what periodic trends means. Like not like exactly what it is, but just what it's referring to. Like what trend.
Yeah. Okay. So as I look here, I'm going to do my best periodic table thing, right? So just periodic trends. As I move from left to right, what happens?
Your atomic number is getting bigger and mass.
Yeah. I'm also adding electrons by and large, right? Except for in the middle, right? And there I am adding them also, but they're not in the valence.
Yeah.
As I move down, what happens? Getting bigger, right? We know that, but they also have some similar properties.
Oh.
Hence the periodic component of that, right? Think about gold and silver and copper. They have some very similar properties. Certainly very, very different than anything that's happening over here with the gases. Okay.
Yeah, that makes sense.
There are some other periodic trends as far as volume of an atom and stuff like that, but we haven't covered that yet. So these are kind of the big ones. And of course, like over here, what's happening, and over here, what's happening, and if I had an arrow like this, you would be able to tell me what those are, things like that.
Mm-hmm.
And you'll be good. Okay. Anything else? Well, I really do. I think you guys are going to do well. I'm very expectant. If not, we'll fix it. We'll do what we can. Okay. So we are going to start some new stuff today, okay? This is where, to me, this is where chemistry becomes chemistry. There's a lot of math. The good thing for you is I'm not a math guy. So I will make the math just as simple, straightforward. Like I had to learn how to make it simple for myself. I will always try to do that for you, okay? Let's see. So we're on chapter 3 now. There's some concepts that we're going to be looking at today. One of them is what we call formula mass. Okay. So a formula, what is that? A chemical formula, what does that tell you? What it's made of, right? What its composition is. And what is mass?
Weight.
It's not weight.
How much it takes.
How much stuff is in there? Weight is a measurement of mass relative to where you're at in the world, relative to gravity, right? You have the same mass here as you do on Mars, as you do on the moon, but you have very different weights, right, depending on gravity, okay? So we talk about formula mass, I'm saying how much stuff, how much mass is in a molecule. So let's look at one. You need your periodic tables. You don't have your periodic tables? You really do need those starting now. They will be indispensable the rest of the year. So this is water. Right? What's water composed of?
Hydrogen and oxygen.
Hydrogen, oxygen. How many hydrogens?
Two.
2. So when I go to find its formula mass, I need 2 times hydrogen, right? I need 2 of whatever that mass is, and I need 1 times whatever the oxygen is, right? So if I were to write this over, I need 2 times what is the molecular mass of hydrogen. 1 point.
0.007.
1 point what? 0079. We're going to stop at the 7, but it's not actually going to be 7, right? Because I'm going to round up.
8.
So I'm going to write 8. All right. So 2 times that, and 1 times, what is it for oxygen?
15.999.
15.999. Okay, I can do this math. This is easy. So I go, this is just going to be 2.016, and this is going to stay 15.999. Now I need to add them together, and I'll have the formula mass for water, right? So can y'all add these together for me? What is it? Need calculate. By the way, that's another thing. We're going to need calculators. I know you can use phones. You're not going to do very well with it like that, though. You need to turn it sideways to get the scientific. I know you can use phones. I'm not going to let you use phones on tests. That will become a disaster. So we need to get just the cheap scientific calculators. They're like $9 or something at Walmart. Okay? We really do need to get those. I suppose that big old boy will work too. Okay, so for now though, use a phone, use whatever, and I need you to just add these 2 together for me. I know this last digit is going to be a 5, right?
2.
It's
0.15.
0.15.
0.15. So the formula mass for water is 18.015. I want to talk about this conceptually for a second. Why? I want to know why it's 18.015 and not just 18. Now, actually, we'll back up one second. 18.015, what? What's my unit here?
Moles.
Not moles, not yet. We're getting there. What am I measuring? Where is this mass coming from in an oxygen atom, in a hydrogen atom? What has mass there?
The protons.
The protons,
Neutrons.
the neutrons, and even the electrons. It's small, but it has mass. We call these the atomic mass unit, right? And that's defined as the average atomic mass of the atomic mass of a carbon-12 isotope divided by 12. Okay, so this is 18.015 AMU, atomic mass units. Well, it's made of protons, neutrons, electrons. I can't have like 0.015 of a proton. That doesn't work, right? And of course, we know that for our purposes, to get this, we're just counting protons and neutrons. We're not even worried about electrons. The mass is so negligible. But there's no such thing as a 0.015 of a proton or a 0.015 of a neutron. So how do I get this? This atomic mass, okay? You're going to want to know this. You're really going to want to know this. Atomic mass number, okay, it is the average of all isotopes of an element. Average of all the isotopes of an element. So we're going to make one up here, okay? But I've got a couple hydrogen atoms here, okay? So one has a proton. That one doesn't. One's got just a proton with an electron. Another one's just got just a proton with an electron. Another one's just got a proton with an electron. And then all of a sudden I got one that's got a proton and a neutron with an electron. This is called deuterium. What's the atomic mass of this one? 1. This one?
1.
This one? This one? 2. So in this sample, what's my total, if I were to weigh this out, how many AMUs would this be? Say 5, yeah. So this is 5 AMU, right? Now I want to know what the average is for any one of these isotopes. So what do I do with my 5 AMU? Divide by 4, right? Okay, and so that would be what, like 1.25 AMU per atom, right? So these numbers are made up and they're not using a sample of only 4, right? They're sampling huge quantities. And to get this, they're taking a sample of a huge quantity to get this average. That's how this is derived, okay? So that was a little bit of a detour, but I think it was helpful to get the concept. So now, let's return to this. What if I want to know what percentage of this mass comes from hydrogen? So that's a question I could ask based off of all this. What is the percent mass of hydrogen in H2O? How would I go about doing that? How do I calculate a percentage?
Yep. It's mass divided by 100.
Okay, so the mass of hydrogen, right?
Yeah.
Divided by what?
100.
Not yet.
100 times the.
I'll get to my 100, but I need the mass of hydrogen done. What am I doing with it? I'm looking for a percentage, right? So I have a certain part, when I'm looking for a percent, I want to know what percent it is of the whole. So I divide the mass of hydrogen by the mass of water, right? And that's going to give me a decimal form. And then to get a percent, I multiply it by 100, right? So that's my formula. This is important. So my mass of hydrogen, right, my average atomic mass of hydrogen should be equals 2. Actually, we already have it, don't we? We calculated that, how much there was. So I don't even have to do that math again. This one stays real easy. So I just get to go equals 2.016 divided by 18.015, right? These are AMUs, right? And then I multiply that by 100, and y'all do the math and tell me what I get.
Seven for 19,
11.19.
19.
What's my unit? It's unitless, right? It's just going to be a percent. Okay. Did you get that same number?
I got 11.99.
11.99?
I
You-
got 11.19.
11.19. I've told you before, and I'll remind you now, this is always my rule for myself. Every calculation I ever do in chemistry and physics and any kind of math, I'm gonna look for the best 2 out of 3. If I get the same answer twice in a row, I run with it. If I get 2 different answers, I'm running it again. Now, if I've got 3 different answers, I gotta take a break, spin around, get a drink of water, figure out how to use my calculator, you know. But it stinks to get a point wrong because of a calculator error. So double check those things. Okay, so this is great. We figured out percent mass of hydrogen. Can I do oxygen? Sure I can. I can do the same thing. There's 2 ways to go about this, okay? Don't write this down. But I can just do the mass of oxygen over the mass of water times 100, right? I can get my calculator and I can do all that. Or I can just go, well, there's only 2 things here. And it comes up to 100%, so this has to be, what, like 88.81% or something like that? Is that right? Yeah, and to me that's easier, so I would do that. Great. Well, let's try something else. Let's do another example. Okay, let's do ammonia, NH3. So I want the molecular mass or the formula mass. Let's do formula mass, I guess, for now. Do molecular mass coming up. Formula mass of NH3, right? So I know that's 1 times nitrogen and 3 times hydrogens. What's the mass of nitrogen?
14.007.
14.007. What is it for hydrogen?
0.008.
Can you say that one again?
1.008.
1.008. So this one's good. I need to run this math, right? So it's going to be what, like 3.024? Don't check me there. I am not to be trusted with math.
Yeah.
Okay. So I add these 2 together, right? 14.007 plus 3.024, and that should come out as 0.031, and that's going to be 17. So 17.031. Okay. So that's how I come up with my formula mass. By the way, what are my units here?
AMU.
AMU. Good. Atomic mass unit. I'm not always good about labeling my stuff. You need to be. So stay on me. Now let's do a quick percentage. Okay, let's do nitrogen. So I want to know the percent nitrogen in NH3 by mass, okay? So to do that, what do? What's my formula?
Mass of nitrogen divided by the mass of NH3.
That's it. So becomes pretty easy. 14.007 AMU divided by 17.031 AMU. And what do I have to do with this? Because I'm not done, right? Multiply by 100. And y'all let me know. It's going to be like 0.9 something probably. 0.8 something.
$82.24.
82.34. I said 0.9, so I got the 100.
24.
Okay, so then what is my percent hydrogen?
70.36. 36, no.
Will be 36, so it'll be 76?
76.
Is that right? Perfect. Okay. Well, that's great. That's a very strong indicator for what's coming up. Anything else off this page you need? You got that all day. Killing me. Okay. Yeah. So they want, it's time to introduce the concept of a mole. So we've been dealing with, to this point, we've been talking about like formula weights or formula masses, right? So a formula mass will tell me the mass of one molecule, right? How often do we deal with like one molecule? That's incredibly small. And how do I deal with masses of very large things? And what if I want to know how many molecules are in very large things? How can I do that? Well, the mole is really the answer to that. It will help us to find those things. So I'm going to show you a quick video. All right, let's go here. This big.
The concept of the mole is something students around the world struggle with. By the end of this video, you should have a pretty solid understanding of the mole and how it's used in chemistry. See, a big part of the problem is that the mole can be thought of in two different ways, and nobody tells you this. The mole can be used to count the very small, things like atoms and molecules. We call these particles. And it can be used for the very large, things that we can see and sense, mass and volume. The mole is useful because it lets us connect and move between these two worlds, the micro and the macro. This is an important idea in chemistry, and as a student, you'll work a lot of problems converting between molecules, moles, and grams. One way to visualize the most common conversions that you'll need to do as a chemistry student is to use something called the mole map. Just like our earlier visual, you can see that the mole is at the center and allows us to convert from things like mass and volume to the very small, counting particles, molecules, and atoms. So here's a pretty typical problem. How many molecules are there in 36.04 grams of H2O? To solve the problem, we have grams, we can change grams to moles. And then once we have moles, we can change that to particles, molecules of water. Again, the mole is our bridge between the micro and the macro. The idea of particles and mass is actually built right into the periodic table. The table, it lists the mass of 1 mole of each element. For example, 1 mole of carbon, that's 12.01 grams. 1 mole of helium, 4.00 grams. We can have the molar mass of a molecule by adding up the individual masses for each element. This is called the molar mass. which we use when we convert from moles to grams. Pause and find the molar mass for SO2.
Let's do that. Molar mass for SO2. So what's the, for sulfur, what's the, how many AMUs is it?
32.065.
32.065 for sulfur. Okay, and for O2, for oxygen, it's 2 times 15.999. So I add those two things up, right? And what do I get?
$64.063.
64.063. Anybody else get that same number? Now the thing here is, we're dealing with grams and not with atomic mass units. Because we're not talking about how much does one sulfur atom weigh on average anymore. We're saying what's the average mass, or use the word weight, and what's the mass of one sulfur atom individually, but we're saying what's the mass of 1 mole's worth of sulfur atoms. And I know we haven't defined like how many atoms are in a mole yet. That's coming up real quickly. But there's a direct relationship between the number of the value of the AMUs and the value of the grams of 1 mole. Okay, this is worth understanding. 1 mole of hydrogen has the same number of individual atoms as 1 mole of oxygen, which has the same number of atoms as 1 mole of nitrogen. A mole is always the same number. Now, they'll have different masses, right? Because oxygen is just a whole lot heavier than oxygen is. And if we were to stack them up on a table, a mole might look much bigger because maybe it's less dense, or maybe it's more dense, but they're going to have the same number of atoms in them, or particles, as they're describing it here. Okay, let's go ahead with this for a minute.
So what exactly is the mole? The mole, it's the official SI unit for amount of substance. It's just a unit, like mass has a unit of grams, or distance has a unit of the meter. So the mole itself really isn't what we're interested in. What we're interested in is the idea of the amount of substance. The mole is just the unit. The idea is the amount of substance. The definition of the mole has changed over time. The current definition has the mole as the amount of substance that contains exactly 6.02 and some numbers times 10 to the 23rd particles. You might know this as Avogadro's constant.
Let's go back to that. We do need to know this, okay? He said several important things there. So he said that 1 mole is the unit label for exactly 6.02214076 times 10 to the 23rd particles. And I'm going to tell you right now, you don't need anything past 6.02. You need to know this, and you need to know this. Okay, 6.02 times 10 to the 23rd. And this, 6.02 times 10 to the 23rd, is called Avogadro's number. Written after the gentleman who hypothesized it. His name was Amadeus Avogadro, and he was Italian, and he basically hypothesized that if I had a certain amount of, or a volume of gas A and a certain volume of gas B and a certain volume of gas C, they would all contain the same number of particles. And he ends up being correct, but it isn't proven for much longer in the future. And this is that number, right? So here it's how many individual atoms there are in this thing we call a mole. We can think of it a different way. You could think of it another way. If I wanted to count if I had a dozen donuts and I had a dozen sheep and I had a dozen horses and I had a dozen children, that'd be way too many children. Like a dozen is just a unit, right? It's just a unit to say they're 12. That's all it is, and that's all that Avogadro's number is. Except it's a unit for a huge number. Huge number, right? I mean, you think about how big this number is, 602214076. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's how big that number is, right? That's a big number. So we just go 6.02 times 10 to the 23rd. This is why scientific notation is really, really useful for us. Let's let him keep going here.
Avogadro's constant. The mole is the bridge between the micro and the macro, counting particles and things like mass and volume. But let's...
I'd like us to have this. I think this is really, really helpful. Wish that I'd had this when I was in chem. So this is showing my relationship, how I can move between different things. A mole, this unit, right? It helps me move to grams. Helps me move to particles. And with gases, at least, it lets me move to liters or volume, okay? And I just do that by multiplying or dividing, right? So I can multiply here, or I can divide here by 22.4. Let me show you just this one. Do me a favor, just stop whatever you're doing, look at this. 1 mole of any gas at standard temperature and pressure, I multiply 1 mole times 22.4, and it'll tell me how many liters I have. So if you're wondering, well, how much volume at standard temperature and pressure does 1 mole of oxygen gas occupy? It occupies 22.4 liters. And if you're like, well, I've got 11.2 liters, how many moles is that? Well, I just divide by 22.4. And then, once I know how many moles it is, I can find out actually how many individual oxygen molecules there are in 11.2 liters of oxygen in a tank, because I can go from moles to particles, right? And so what I do here, I'm going from one to the other, and I multiply or I divide, just like it said, and I multiply by 6.02 times 10 to the 23rd. So if I had 11.2 liters of gas, that's a half a mole. I multiply half a mole by that number, and all of a sudden I get 3.01 times 10 to the 23rd particles. That would be a very typical type of formula that you'd be asked. Is how many molecules of oxygen gas are there in this number of liters? Okay? How do we feel right at this moment? So far so good? Okay. This diagram is so helpful. And then we do the moles to mass or moles to grams thing very easily, right? Just by multiplying or dividing. If I want to go from moles to grams, then I multiply by molecular mass. Okay. So let me hit play here. We'll see what else he's got, and then we'll do our own problems.
Related to a chemical equation. So here we have the formation of water from hydrogen gas and oxygen gas. We could balance the equation like this, and we can think of the coefficients as moles. In fact, we think of them as a mole ratio. So we have 2 moles of H2 plus 1 mole of O2, we get 2 moles of H2O. And we can use this ratio to solve more complex stoichiometry problems. To wrap up, the mole helps us work with mass, molecules, and balanced equations. Now that you have the big picture, you need to learn the mechanics of converting between moles to grams and using the mole ratio with balanced equations. There is in the description of this video to help you do this.
Okay, by the way, I always put these videos on the actual website, right? So if you wanted to go check out what he's got, then that would be good for you to do, and not hard. Let's go back to this. Okay, so I'm going to give you a practice problem. I've got 38 grams of H2O as a liquid, okay? So this is just water. I want to know what is the volume, if I turn this into steam, what volume is it going to occupy, right? So how would I set this up? What do I do?
You need to find the molecular mass.
Okay, so I've got 38 grams. Well, we'll save that for a second. We are going to do that. 38 grams, what's my equation going to look like? 38 grams times what? I'm going to go from grams to what? That's where I'm at here. I'm here and I want to go here, right? So I go grams to moles. So to do that, I multiply it by my molecular mass per mole, right? So this will be my molecular mass, or my formula, yeah, my molecular mass. And what's this going to be?
22.4.
Well, no. It's my molecular. I need a conversion factor.
Oh,
Okay, so it's going to be grams per mole. So this is molecular mass in grams per 1 mole. Okay, because I want to go from grams to moles. This equation will let me do that. And then I want to go from moles to liters. So then I'm going to multiply that by what?
22.4.
Yeah, so what goes where?
moles.
Moles is on the bottom. I need those to cancel. So 1 mole, and this is going to be
22.4 liters.
22.4 liters, and that will set me up. And I'll have my answer in liters. So I'm going to replace this here. My molecular mass of water, we've already calculated that, right? 2 of hydrogen, 1 of oxygen. What did we calculate that to be? 18 point something? 18.015. So I can plug this in to a calculator, more accurately you can. And what do you get? And let me ask you this. Y'all know to just like multiply everything on the top and then divide by everything on the bottom, right? Just to keep it super simple. Okay. So run the math and tell me what you get.
$47.34.
47.24 liters. Okay, somebody else confirm. You got the same answer? Good. Good. It's a lot. Think of a 2 liter of soda, right? So this would be roughly 24 2 liters of soda worth out of just 38 grams. That's not that much. Right? Just makes you think about density. Like, it's the same amount of water, there's the same number of particles, whether it's liquid or whether it's a gas or even whether it's solid, but very, very small, relatively speaking, volume here, huge volume here, right? Gases just take up a lot more space. Now, I said that it's going to be the same number of particles. I want to know how many particles those are. How many particles, how many molecules of water are there in 38 grams of water? So I'm not going to steam anymore. I want to know how many atoms, or how many molecules. Run the math. How do I set this up? I want to go from mass to particles. So what does this say to do? Divide by molecular mass. So I'm going to put my molecular mass down here. What is that molecular mass? 18 point what? 0.15. That's for 1 mole, right? And now I want to get to particles, so what do I do? Multiply by 6.02 times 10 to the 23rd. Fix my units. Y'all run this math for me.
times 10.
12.69 times 10 to the what? 23rd. You'll get that same answer?
Yeah.
Yeah, okay. Okay, well, that's great. This is gold. Don't lose that. So, we probably need to look at some terms, some definitions, just so we've got them, okay? I'm not going to erase that. I like that. Okay, so a mole. Okay. Mole is just flat out 6.02 times 10 to the 23rd particles, right? That's one definition of it, is its relationship. That's just how many things there are, right? Another concept, and it's molar mass. It's the, I guess we could just say it's the mass of that many particles. Another way we can look at molar mass is it's the atomic mass, or the formula mass, expressed in grams. What's the mass? What's the molar mass of oxygen gas? There's a trick in there, okay? It's an oxygen gas. What am I indicating to you? How should you be thinking when I say oxygen gas? I want mass. How do you think you'd calculate this? Where would you go to find it? Okay, so tell me.
15 point.
You'd think 15.999. Catch is oxygen doesn't exist monotomically. Oxygen has 6 valence electrons, it wants another 6 valence, it wants 2 more, so it'll bond with each other. When I talk about oxygen gas, I'm talking about this. Oxygen double bonded with itself. Okay? So it's not 15.999, it's going to be 31.998 or something like that. Do the math,
Is 002?
because it's diatomic. Gases are always diatomic.
31.998.
Huh?
31.998.
Okay, so it equals 31.99.
So you're essentially just adding both of those weights?
Because it's O2,
Yeah,
because oxygen exists as O2, then I've got to double it, right, to get it.
okay.
Okay. I would like for this one, you can all just look at your notes. I would like the molar mass of ammonia.
17.031
17.031 what?
AMU.
Not AMUs. That was the formula mass, or the formula weight. I want to know the atomic, or excuse me, the molar mass.
Grams?
So just be in grams. The numbers are the same,
Which
but it's going to be in grams, because molar mass is defined as the grams per mole, right? Or the grams that that number of particles takes, will have.
So would you just double it again?
No, you're not doubling it. It's the same number.
Just
The unit is just different.
Oh.
Instead of AMUs, now it's going to be grams.
Oh,
Okay.
okay.
Give me the molar mass of water.
18.015 grams.
Okay. So molar mass is the mass of 1 mole. Molar mass is the formula mass in grams. And that's what we just looked at. You already had those formula masses, and now we just expressed them in grams. Okay? So that part clicked. That's good. Y'all are doing great. That's just easy. Okay. It's a problem straight out of your book. We'll just work it here, and then later on, if you, hey, how do I do this? You can either check this, or you can check your notes, you can check the book. So, it says, according to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. Question is, how many moles of potassium do you need, right? So I want to go 4.7 grams of potassium to moles of potassium. What do I do? How do I set this up?
4.7 times 1 mole over the
4.7 grams times 1 mole over
the molecular mass.
molecular mass. So I need my molecular mass for potassium. And then
39.098.
30 what?
9.
39.098.
098.
So I need you guys to run that math. I'm going to go grab a cord so my computer doesn't die. Anybody got a number for me?
0.12.
0. What?
12.
0.12?
Yep.
Okay. Did you guys get that?
Yes.
Awesome. Okay. Okay, so this next problem says a liter of air contains 9.2 times 10 to the negative 4th moles of argon. Okay? We're gonna say at STP, by the way. We're gonna do a double whammy out of this problem. So the first thing I want to know is how many grams of argon will this be? Okay, so grams equals. I'd also love to know how many atoms. And then finally, I'd like to know what percentage of the gas is argon. So how do I do my grams? I want to go from moles of argon to grams of argon. So what do I do?
Multiply by the mass.
Multiply by the formula weight, right? So 9.2 times 10 to the negative fourth moles, that's a tiny little amount, times
39.948.
39.948. Now this one I don't have to double. Argon will exist monotomically because it's a noble gas. It doesn't play well with friends, it doesn't bond, right? So when I multiply those two things together, what do I get?
$367.5216.
367.5216 grams.
Yeah,
Okay, you'll get something similar?
but it's times
Oh,
10.
okay.
Yeah, I didn't put the times 10.
Times 10. It's
Yeah, times
367 point that.
Yeah, times 10 to negative 4
Okay,
grams.
but if I'm going to do the true scientific notation, I want to move this back to, so I should get 3.67 or so times 10 to the negative 6. Do you guys get something like that?
I got 0.037.
0.037, what'd you get?
My calculator wasn't working.
Okay, well we're gonna run, let's all run this one more time, okay?
Oh, there you go.
Mine will just work. Let's- Okay. You get 0.0367. Of course, if I want to put this in scientific notation, it's going to be 3.67 times 10 to the what? Or negative second, right?
Yeah.
1, 2. Okay, so that's my grams, okay? Now we're going to run some other calculations. I want to know how many atoms there are, okay? Do I have to deal with my grams? No, I can stay with my moles, right? So I got 9.2 times 10 to the negative fourth moles. And to go from moles to particles, what do?
Like
Multiply by 6.02 times 10 to the 23rd. Oh, I hit the wrong button there. What'd y'all get?
That's 5.384 times 10 to the 20.
5 point what?
5.5384 times 10 to the 20.
Okay,
Yeah.
good, okay. Now, this last one is a bit trickier. What percentage of the gas is argon? So we had 1 liter had 9.2 times 10 to the negative 4th argon. I want to know what percentage of that liter is argon. To do that, I need to know, first of all, how much should be in any given liter, right? So I've got 1 mole. I want to know, I've got 1 liter. I want to know how many moles should be in 1 liter. Maybe this is 100% argon. Maybe it's 50% argon. I don't know yet. So I want to know, I have 1 liter. I want to know how many moles that should be. So what do? I'm here. What do I need to do?
It's gonna be divided by 22.
0.4. Okay, so do that math. What do you get?
0.04.
Between scientific notation.
4 times 10 to the negative
Second, right? Go get something like that. Divide 1 by 22.4, right? That's all I do to this point. So 1 divided by 22.4 equals 0.446. In scientific notation, that's going to be 4.46 times 10 to the negative 2nd, right? Now, that's how many, oh, I wrote liters and that should be moles. Maybe that's what got me all confused. Bless my heart. So that's the number of moles that should be there, right? But I have 9.2 times 10 to the negative 4th moles. So I want to know what percentage of this is that. So how do I do that equation?
Would you divide the 4.46 over?
Nope. Exactly backwards.
So the 9.2 over?
Yep. So I'm going to go 9.2 times 10 to the negative 4th moles of argon divided by 4.46 times 10 to the negative 2nd moles of total. All right, run those numbers, tell me what you get. And don't forget to, I'm sorry, also multiply by 100, right? What'd you get?
I got 2.06.
So I got 2. So only 2% of whatever volume of 1 liter of gas there is actually argon. Okay. I have gone so far away from my notes, it's not even funny, but it's good. Am I okay to erase? Okay. We're gonna get a new topic. All right, we want to determine empirical and molecular formulas. been doing percent composition. Done that quite a bit. Let's do, we'll do this problem. Let's see. Yeah, let's do it. Okay. So I have a 12.04 gram sample. You put that joker through mass spectrophotometry, which will tell you how much of each thing you have. You don't need to worry about all the details of that. And at the end of it, you find out that out of this total, 7.34 grams are carbon, and 1.3585 grams, 1.85 grams are hydrogen, and 2.85 grams are nitrogen. So what is the percent? We don't need to do this, do we? You can do this in your sleep. We've been doing this, right? We just did it at the atomic level instead of at this level. Let's move forward. Let's go to empirical formulas. We haven't talked about empirical formulas yet. Still not, probably not. Okay. So empirical formulas are the simplest whole number ratios of a molecule. Let me give an example. Hydroxide, H2O2. Okay, it looks like this if you were to show it. If you were to bond it. Looks like that. Okay? H2O2. But that is not the simplest whole number ratio, right? I can simplify this, yes? So what might be the simplest whole number ratio of this? What's my least common denominator for H2O2? 2. So if I divide this by 2, what do I get? HO, right? So that's my empirical formula. It's basically just showing me my ratio of hydrogens to oxygens. I cannot use an empirical formula to try to determine my formula weight. I can't use it to run calculations. That would be very dangerous. It won't tell me how the atoms bonded together. What it's simply going to tell me is my ratio of these molecules to each other. Okay? Let's do another one. Let's do C6H12O6. This is glucose. Okay? That's my correct formula, molecular formula, but it's not the correct empirical formula. What's the correct empirical formula? CH2O. I divide everything by 6, and I will get CH2O, right? By the way, that's why these are called carbohydrates, because I've got my carbon, and I've got my water, carbohydrates. You were wondering where that name came from, okay? Let's do another one. So you did some calculations and it looked like something came out like this. Hold on. I went too far in my head and messed myself up. Something I find has 1/3 of its atoms are nitrogen, or 0.33 nitrogen, and then H is 1. That's not an empirical formula, right? Because that's not a whole number. What would I need to do to turn that into a whole number for an empirical formula? I need to multiply it by a factor of 3. 3 times 0.33 will get me to 1, right? So this times 3 equals NH3, and I'm back to ammonia. Let me give you another one like that. Do that one. I've got to multiply, I can't divide, right? Because I've got these decimals. My decimal is 0.5, what do I need to multiply everything by? Not by 5, by 2. 2 times 5 will give me 1, right? So if I multiply this by 5, or if I multiply this by 1, then it's going to give me CH2O. Just for fun, let's do this by 5 and see what we would have got, okay? If I multiply it by 5, then I get C 2.5, right? H5, O 2.5, and so I still don't have a whole number ratio. But I could have multiplied it by like 4. That might have got me somewhere. If I did that, I get C2, H4O2. At least I'm in whole numbers. Now what would I need to do? Divide by 2, and I'd get CH2O, and then I'd be there, right? There's a reason I'm showing you this. You're going to have to do this stuff in chemistry fairly often. And sometimes you just have to like throw stuff at the wall and see what sticks. Like you're just going to have to try stuff. Multiply it by 3, multiply it by 4, divide by this to figure it out, because you're going to get these, after you do your calculations, you're going to get these ratios, these percentages, these decimals, and you aren't always automatically going to see the relationship between them. So just try stuff, okay, until it clicks, and then, all right, it's some of the best advice I can give you on that. Now let's go back to this idea of an empirical formula, and let's do something with it, okay? So these are simplest whole number ratios for a molecule, right? Very useful for some stuff. Certainly for percent compositions, etc. Not useful for everything. Okay, so it's giving us 1.71 grams of carbon, and it's giving us 0.287 grams of hydrogen. I want to come up with an empirical formula out of that. How can I approach this?
Let's work in moles.
Okay, let's convert it to moles. So 1.71 grams of carbon times how much per mole? Give it to me. Should be like 12 point something, right?
12.011.
It's 12.011. Okay, so let's do that math. What do I get?
Zero 0.1423.
23. Okay, moles of carbon. All right, now let's come up with moles of hydrogen. So I've got 0.287 grams of hydrogen times 1 mole of hydrogen over 1 point, what is it?
0.007.
0.008. Okay, and what does that come out to be?
0.2847.
0.2847 moles of hydrogen, okay? Now I want an empirical formula out of this. There are a number of ways that I could go about this. Frankly, right now I can look at it and I can see it. You may not be able to just look at it and see it. One thing I could do is figure out the percentage of one to get a ratio, right? So I can add these two together, and that would give me, somebody add the two of them together.
Zero point 427.
0.427. So if I want to know what percentage of my moles are, not just the number of moles, but the percentage of moles are carbon, I just need to divide by that, right? So I take 0.1423 moles and I divide it by 0.427 moles. I multiply 100 and I get
3.33.
how much?
3.33.
3.33? That right?
No, I think no.
Didn't sound right.
It's 33.
Okay.
33.3.
That sounds much better. 33.33. So if that's 33.33, then what does this other one have to be? So I only got two things. I don't even have to do the math again, right? This is 1/3, so what does this have to be? 2/3. It's got to be 66.66. 1/3 to 2/3. What's my ratio? It's 1 to 2. This is a 1 to 2 ratio of what? Carbon to hydrogen.
Yeah, they should have probably carpet there.
Feel good? Now, I told you before, I can look at it and see it. Part of that's just experience. But if I look right here, and here, I can see a relationship, right? 28 is twice what 14 is. So I look at that and I go, oh yeah, that's double. That's a 1 to 2 ratio, right? But you may not see that right away. And it's good to be able to get at something multiple ways. It really does help. And let me just double check. I'm sure that is what this answer is going to be. It is. It's CH2. Where are we at on our time? We are actually 1 minute over and we didn't quite finish. But that's okay. So we'll pick up here next class. We're going to take a test and we'll finish like 1 or 2 examples out of this. And that'll be that. Okay.
All right, thank you so much.
I can't imagine the test is going to take you an hour, but we'll plan on having an hour. Okay? Bring a calculator. There's like a couple simple math problems. There's more than a few math problems, but most of them, honestly, you don't need to calculate. It's just conceptual. Like you'll be able to visualize what the answer is. Bring a calculator. Study your stuff. You know how to get a hold of me if you need me. I forgot to pray before we started, so can I pray for us now? Father, thank you for this day and for the understanding that you've given us with all of this. I pray that you would help everybody in this class to really grasp the things that they've studied, to have a good sense of themselves and where they're at, and be motivated to study the things that aren't understood very well yet. And we pray for those who are not here, that they too will be prepared and that they'll get these notes and hang on to these things. We praise you for who you are and what you've done in Jesus' name. Amen.